Good morning, everyone. Today we are going to learn about the program of computer networks that is related to CRC, that means Cyclic Redundancy Check. So this Cyclic Redundancy Check program, this will be in different types of polynomials like CRC 12, CRC 16, and normal CRC and CCIP. So using all these polynomials, how we have to compute the CRC code using C language program. Okay, let's see. Before going to the program, we have to know about what is cyclic redundancy check. Okay, so here when coming to the background of CRC, it was developed by and invented by Wesley Peterson in 1961. So it is commonly used to detect accidental changes to data transmission. So, for example, suppose if any one of the system, so from any one of the host, if you want to transmit some data, then in between there will be some disturbance. So that disturbance can be related to any noise or any other network device problems, router problems, gateway problems, or any kind of problems will happen. So at that time the data might be changed. So that accidental changes while transmitting from one host to another host, if any changes happened or data might be changed, so at that time how we have to detect that kind of errors. So that detection can be possible through CRC method. Okay, that is possible through CRC method. So actually the this CRC is involving by binary code. It is involving by binary code. Okay, so all the data bits which are coming from source to destination by using polynomial divisor. Polynomial divisor. Okay, so so that we can call it as polynomial code checksum. So CRC is also called as polynomial code checksum. So before sending the message over the network channels, the sender encodes the message. So first of all, the sender must encode the message at the sender side, and and then the sender can send the message to the destination, I mean receiver. So at the receiver side, if receiver can accept the data with any errors, then immediately it can detect it. If you are using CRC method, it can easily detect whether there is an error or not. If there is an error, immediately it will detect. Okay, if it is error free, then the receiver easily accept that information. Otherwise he may discard the message, and he asked to the receiver will ask the sender to resend the same information because of that error detection. Okay, so this is about CRC. Then next, so this is the process uh, related to the CRC encoder and decoder. See here, in this data segment, so this data segment is in the form of zeros and ones. Okay, so it may be a data which is sending by the center. I mean, whatever the data is there, that data uh, converting into the bits format, and then that can be considered as a segment. So that segment we can convert into the uh, encoding format. So that encoding format can be assigned by, can be calculated by polynomial code. Okay, so polynomial code will be dividing by this data segment, then adding of these reminder bits with the message bits. So that reminder, whatever the reminder bits will come while dividing by this polynomial of this data, so that uh, reminder bits will be added right side of the message, right side of the message bits. So this is the message bits and this is the polynomial divisor. So when you divide the data with this polynomial, then we will get reminder. So that reminder is considered as CRC bits. So these CRC bits we can add after the message bits. Okay, then after adding CRC bits with this message, then that will be transmitting through this computer networks. Then through this network, what the message is transmitting to the receiver, so that can be that sometimes it may corrupted. So if this is the receiver side, so at the receiver side, if the decoder, if the receiver can catch any errors or can detect any errors by corrupting the messages. So if any corrupted messages are there, then receiver immediately can detect by using this CRC decoder. So here also, whatever the message, see this message, so this message, the complete message is dividing by this polynomial divisor in the decoder, in the decoder. So at this time, if all zeros are there for the, if all zeros are there for the reminder, then the data will be accepted. Otherwise, the receiver can send a message to the sender to resend the same information. Okay, this is the process inside the system. So how we have to compute the CRC? So this is the same what we discussed earlier, the same way here also. When messages are encoded, if any message is encoded using CRC, so uh, what for this encoding message, we need one message, we need one message as well as polynomial divisor, polynomial divisor. So this polynomial divisor, we have to, we have to make division, we have to do the division by this polynomial divisor with this message. So while doing this one, how many bits, what is the degree of polynomial, that many degree of zeros we have to add with this message. So then only it is we have to do the division. Okay, then that is the first step. And coming to the next step, the value of value is mutually agreed upon by the sending and the receiving parties. Both can be uh, participated, both can be mutually agreed upon the values. So that is like k bit word, k bit word, that means message is k bit word, is represented by a polynomial which ranges from x power 0 to x power k minus 1. So k bit word, suppose the message is there, polynomial values will be k bit word. So this k bit word can be maintained by the polynomial codes that can be x power 0 to x power k minus 1, x power k minus 1. So up to this we have to make one polynomial. Okay, so the order of this polynomial is power of the highest coefficient, that is nothing but k minus 1. So k minus 1 will come first, like this, k minus 1, then x power k minus 2, so up to k power 0. Okay, so the length of g of x should be less than the length of message it encodes. So it should be less than the length of the message. So always the polynomial, suppose here suppose the message is in n bits, so n is always greater than the polynomial length of k. Okay. And uh, also both the most significant bit and least significant bit, so both msb and lsb should be 1 only. In this process of encoding, CRC bits are appended. So we have to append CRC bits to the message so that the resultant frame is divisible by g of x. G of x is nothing but polynomial divisor. So uh, how many bits? How many bits are there with the polynomial divisor? That minus 1 bits. Suppose polynomial bits are k. So k minus 1 bits have to be appended by the CR by this message. So that will be considered for the division process. Okay. Next, this is the algorithm for encoding using CRC. So, when coming to the encoding process in the CRC at sender side, the communication parties agrees upon the size of message, that is m of x, and the generator polynomial, that is g of x. So g of x is the divisor and m of x is the message which the sender wanted to transmit. If r is ordered of g of x comma r, so r is order of g of x, so r bits are appended to the low order end of m of x. So that means we have to first of all we need to take message. So message is like suppose the message is this is the example of message, and the polynomial maybe 101, for example 101. So here r bits are the r bit have to be appended at the lower order end of the m of x. So at the end of the message we have to add uh, two zeros, because what is the order of polynomial here? This is x power 0, x power 1 and x square. So order of polynomial is here 2. So two zeros we have to append to this message. That is two zeros we have to append. So that is the second point. And next, coming to the third point, the block x power r m of x is divided by g of x. So 1010110100, this is the this is the message we have to divide by the polynomial, that is 101 sorry 101. Okay, using modulo 2 division. So that is the third step. And coming to the last step, the remainder after division is added to the message using modulo 2 addition. See, whatever the suppose 101 once 101, and then what is the reminder here? Here we have to do the XOR process. So all zeros unique values are there, then we'll get zeros, and then uh, 0. So this is 0 times, then again 001, that is also 0 times, triple 0, then 01, here 1, 011, again we have to divide with 0 000, then 1 1, then here 0 101 once 101. So here the unique values will be 0 and different will come 1 1, and here also 1, and again 1 time 101, again 10 we'll get, then again 1 we have to make, that means 101, again once 101 we'll get 0. 0 0 0. Again, if you make these two zeros, we have to put like this. So finally, what is the reminder here? 0 0 0. So that reminder we have to add with this message. So this is the actual message. So this message 1 0 1 0 1 1 0 1. So with this message we have to add this reminder. This reminder is triple zero, sorry, two zeros. So these two zeros will be added by this message. Okay, so this is nothing but encoded message. This is encoded message. So this is encoding process. We have to exactly divide by g of x, that is polynomial here. This is the g of x and this is m of x. Okay, these two bits are order of bits, that is considered as r. Okay, so this is the process of encoding, right? Then coming to decoding process. So this is the decoding process. Actually, whatever the receiver receives, encoding process is at sender side, decoding process is at receiver side. So receiver divides the incoming data frame, that is t of x units by g of x using modulo 2 division. So mathematically we can do e of x is the error, and then modulo 2 division of m of x plus e of x by g of x is done. Suppose if any error bits are there, then that can be identified easily. The reminder, the same process what we have done, but what we did in the previous process, like encoding process, the same date, same thing we have to do with the receiver message, with the received message. The same polynomial we have to take, but the receiver, what the receiver will take, that is m of x along with the r bits, that is reminder bits. Okay, so this is again dividing by the g of x, g of x. So when you do this calculation, the final reminder will be all zeros. So if you get like this, then there is no any problem. That means it is acceptable by the receiver. Suppose if any bits are not, I mean, if any bits are having ones, then there is an error. So that error can be detected by this one, by this process. Then the receiver again send a message to the sender to retransmit the same information because of this error detection. Okay, so if there is no reminder, then it implies e of x and data frame is acceptable. So that means all zeros are there, then there is no reminder, so that can be accepted. If a reminder indicates non-zero, that means any one values are there with this reminder, or in other words presence of an error, so that is nothing but presence of an error, so the data can be rejected and the receiver may send a message to erroneous acknowledgement back to the sender for the retransmission. So this is the process of decoding. Okay, next, uh, cyclic redundancy check is a method of detecting accidental changes or errors in the communication channel. So it can use a generator polynomial which is available on both sender side as well as receiver side. So for this, an example, here one example, I'm taking one example. See here, generator polynomial is of the form like this one, x cube plus x plus 1. So in between some 1 degree is missing, that is x square is missing. So at the place of x square we can put 0. So x cube is existed. So at this place we can put 1. X square missing. So 0. X is there. Then 1. And here also x power 0 is also there. Then again 1. So that means what is the polynomial? 1011. So 1011 is the polynomial. Okay. So here one more example. X square plus 1. X square plus 1. So in between we have x square, x1, x1 is missing, and x power 0 into 1. 1 is there. So x power 0 is nothing but 1. So that is existed. So 1 is there, and x square is also existed. So 1 is there. So this is missing. So at this place we can put 0. So what is the polynomial value? That is 101. So here it is, right? Next. So n number of bits in data to be sent from sender side, and k is the number of bits and the key obtained from the generator polynomial. Okay. So at this sender side, generation of encoded data from data and generator polynomial. So this generator polynomial is also called as key. So the binary data is first augmented by adding k minus 1 zeros in the end of the data. So whatever the message sender wanted to transmit, so that message uh, is nothing but m of x, that can be added k minus 1 zeros before doing the polynomial division. Okay, so k minus 1 zeros will be added here. Okay, so these zeros are k minus 1 zeros, right? Then use modulo to binary division. So this division is done by polynomial, that is g of x can be divided here. So using binary data by the key and store remainder of division. So finally whatever the remainder we'll get, so that remainder we have to add along with the message, then we can send to the receiver. Okay, so append the remainder at the end of the data to form the encoded information and send the same to the receiver. Okay. And at the receiver side, it can perform the same modulo division. Again, if the remainder is 0, then there are no any errors. If the remainder is 0, there are no errors, then receiver can accept immediately. Otherwise the data is having some errors, so that data cannot be accepted, that means rejected, and then the same negative acknowledgement will send to the sender for the retransmission of the same data. Okay. So this is the modulo 2 division. So at this modulo 2 division, we have to do the XOR operation for the subtraction of this data. I hope you know about what is XOR division and modulo 2 binary division, right? So in each step, the copy of the divisor is XORed with the k bits of the dividend or the key. Okay, and the result of the XOR operation is n minus 1 bits, and which is used for the next step after one extra bit is pulled down to make it n bits long. So this is same as like our normal division operation, but whenever we want to do the subtraction, so at that time we need to do XOR operation. Instead of subtraction, we have to use XOR operation. So that is only the thing, and remaining are all same as like division operation. Okay. And this is the example with no error in transmission. There is no any error with any transmission. So this is the message, data word to be sent. 100 100. This is the message, that is m of x. Okay, m of x equals to 100 100. And what is the key value? Here, x cube plus x square plus 1. So that means x cube place 1 is existed, x square 1 is existed, but x is missing here. X is missing here, that is x power 1. X power 1 is missing, so we have to put 0, and 1 is there. Then we can put 1. So 11101 is the key value. That means generator polynomial. Okay, this is the generator polynomial. So this we can consider as g of x. This is g of x. So therefore the reminder, see here, how many bits are there? What is the degree of this polynomial? X cube. That means what? 3. So degree is 3. So 3 zeros we have to append after the message at the time of doing this division operation. Then we have to do all the division operations like this. And finally, what is the reminder that can be appended with this message m of x? So m of x plus, I mean appending with r value. That r is nothing but this one. This is reminder 001. So that 001 we can append at the end of this message. Okay, 100 100 is the message and 001 is the reminder. So this reminder we can add at the end of the message. Then this is called as encoded data. This is encoded data. So which can be transmitting to the receiver. Okay. Next, at the decoding side, at the receiver side, the decoding process will be done. So that is the code word received at the receiver is 100 100 001. So 001 already we have added, I mean appended. That is reminder of the x modulo 2 division operation. So that reminder we can append by the message. So that is nothing but the coded encoded message. So this encoded message can be divided again with the same polynomial. So when we do the same polynomial with this message, then we, if you get all zeros at the reminder side, then the data is not having any errors. So this can be acceptable. So this data is acceptable. Okay. Suppose if there is any error is there, then how we have to find? See here, the same process is done here, 100 100, and the key is 1101. That means x cube x square plus 1 only. There is missing one thing, that is x. Okay, x is missing, so that it is there. And here what is the reminder? 001. So the same thing is appended by the message, and this can be sent to the receiver. So at the time of receiver, receiver side, the receiver may receive a message like this. So one bit missing here, 100 100. Instead of that, all zeros, and finally 1 is there. So at this time, here there is an error. How we have to find this error? By using this polynomial division check here. See, 1101 is the polynomial generator. So that can be dividing this one. Okay, so this if you divide this message with this polynomial, then instead of getting all zeros, we'll get 011. So the 011, if there is any non-zero elements occurred at the reminder side, I mean a reminder, uh, uh, we have to reject this information, and also we have to send the negative acknowledgement to the sender for the retransmission of the same data. Okay, so there is no not all zeros, reminder is not having not all zeros, so that this can be deleted, detecting the error at receiver side. Okay, this is the way we have to find the error, I mean detect the error. and here it is the sample output for your program. So data maybe 100 100, key is 1101, and the encoded data will be data along with the key. This can be encoded. After encoding the data, what is the reminder? 001. So that reminder we have to add with the data, then that can be considered as encoded data. So this is the encoded message. Okay. So at the output, I mean, at the this is at the sender side. At the receiver side, the same is encoded data is coming to the data part, and key is the same value. Here decoded of data with data and key. Okay, so this data is encoded data that can be divided by using this key. So if the remainder is all zeros, then the data will be accepted. Otherwise, it can be rejected. Okay, that is the output of this program. I mean, this algorithm. Okay, so when coming to this CRC 12, CRC 16, CRC CCIP, when coming to this polynomials, CRC 12 means the 12 degrees. 12 degrees will be existed in the polynomial. See here in the generator polynomial, this is power 0. So this is x power 0, x power 1, x square, this is x cube, x to the power of 4. Okay, so here x cube and x square is missing, so that here we will not writing any, we will not be writing any polynomial here. X to the power of 4, x plus 1. That means 2 are missing, these two are missing, so that two zeros we can put. Okay, here x cube is missing and x square is also missing, so in that place we can put two zeros, and x place we can put 1, and 1 place is also 1. So this is the generator. So this means the CRC 4, this is CRC 4. Okay, right? So what is CRC 12? So the degree of CRC polynomial will be 12. Okay, see here CRC 32, that means the degree of polynomial will be x to the power of 32. Here x to the power of 26. So like this way, we can have the generator polynomials. So CRC CCITT. So at this time we have the data, I mean the polynomial data is coming from x to the power of 16. Okay, and CRC 8 is nothing but like this. This is the polynomial x to the power of 8 plus x to x square plus x plus 1. CRC 12 means x to the power of 12, x to the power of 11. So like this way. And CRC 16, x to the power of 16, x to the power of 15, x square plus 1. So the polynomial the generator polynomials will be constant values for this CRC 32, CRC CCITT, CRC 8, CRC 12 and CRC 16. So whatever the CRC you are using, the generator polynomial will be changed. That's it. And remaining are all same. The process is same. Like whatever the message is there, that message is greater than the polynomial generator polynomial. The message should be greater than the generator polynomial. That should be considered for the division. If it is less than the, it is not possible to do the division. Okay, so this is all about CRC process, right? Yeah, thank you for watching.